All right, welcome back to the last topic of week 2. In this section, we're going to talk about proof by contrapositive. So in the book, 3.2 covers a really wide variety of proof techniques other than direct proof. The chapter is just called indirect proof. We're only in this section going to talk about one of them, which is proof by contrapositive. And in particular, proof by contrapositive is going to be the last thing that is going to be on the test on this Friday. So there will be questions about proof by contrapositive on the test, but nothing beyond that. We'll save that for next week. Okay, so remember what the contrapositive of an implication is. If I have the implication P implies Q, the contrapositive is not Q implies not P. And there's one really important thing about the contrapositive, which is that it's logically equivalent to the original implication, as we showed back in the first section. I've tried to really emphasize this, so if you recall, there was this question on the homework last week that gave you a bunch of theorems and asked you to write down their contrapositives, and then asked if the contrapositives were true. The point of this was just to reiterate to you that, yes, if the original thing is a theorem, that means it's true. Its contrapositive is also true, because contrapositives of true things are true. That is what this logically equivalent business means. And so, roughly speaking, the whole idea of a proof by contrapositive is if you're asked to prove an implication and you don't like the implication, maybe you like the contrapositive better. So, here's really the only new idea in this section. It's sufficient to prove the contrapositive of an implication instead of the implication itself. So let me show you some examples where this is really helpful. So let's let x be an integer. And let's prove that if x squared is even, then x is even. Now, if you try and prove this by direct proof, it gets kind of messy. Because what do you get? You learn that x squared is 2k for some k in z. And then somehow you're trying to say something about x, so maybe you try taking a square root, and now you get x is root 2k. But now this thing probably isn't an integer anymore, and so mass confusion ensues. So if you try and prove this directly, that is, if you suppose x squared is even, and then try and somehow get to x is even, it's going to go pretty badly. But, as you would probably guess from the title of the section and my introduction, it goes much better if we prove the contrapositive instead. Every time you're going to prove the contrapositive, instead of the original implication, you need to make the first sentence of your proof something to tell the reader that. I will usually go with the old standby, we prove the contrapositive. But, also, you have to tell the reader what it is you think the contrapositive of this statement is. Do not make the reader do it in their head. Instead, write out the contrapositive that you're about to prove. In this case, it is, if x is odd, then x squared is odd. So that's two musts right off the bat. If you're doing a proof by contrapositive, you have to say that, and you have to say what the contrapositive is. But good news, as soon as you write out the contrapositive, you're just doing a direct proof. So now I'm proving if x is odd, then x squared is odd, and I get to do that exactly like we did in the direct proof section. So we're going to suppose x is in z, and x is odd. So then that means there exists a k in z such that x is 2k plus 1. So x squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1. And so if L, say, is 2k squared plus 2k, then x squared is 2L plus 1, so x squared is odd. And so what have I done here? I've shown if x is odd, then x squared is odd. That's exactly what this piece of the proof says, but that was the contrapositive, so I have now proven the original claim. And so I can write my proof box and go home happy. Please note, you should not be writing significantly less in your proofs than I am. Everything in a proof should be part of a sentence, just as this is here, you should definitely not just grab pieces of these equations and write them down. It will not work well. You need to be writing at least this much, possibly more, in order to be getting credit for your proofs. So make sure you're sort of adopting a style for proofs that involves writing, because there will be lots of writing. Let's prove that if 3x to the 4th plus 1 is less than or equal to x to the 7th plus x, then x is greater than 0. Here, x is a real number. Again, you should be looking here at what would tip you off that you should look at the contrapositive of this. And the thing that should alert you to the fact that you probably want to prove the contrapositive is that if I look at the if part of this, if I use direct proof, this is the thing I get to assume. And I then somehow have to use this mess in order to say something about x being greater than 0. I'd rather generally assume the simple part and get to the complicated part. So I don't really want this to be my hypothesis. And so in order to fix that, of course, we prove the contrapositive. And what is it the contrapositive says in this case? It says that if x is less than or equal to 0, then 3x to the 4th plus 1 is strictly greater than x to the 7th plus x. So let's proceed. So we're going to suppose this part. So x is non-positive, and I want to think about what that tells me about x to the 7th plus x. Namely, if I have a non-positive number, and I raise it to an odd power, what happens? Well, I get a non-positive number again, right? So because both this power 7 and this power 1 are both odd, this thing, in fact, is negative when x is less than or equal to 0. If x doesn't happen to be 0, then this thing is strictly negative, but even if x is 0, this thing is still less than or equal to 0. On the other hand, let's look at this other piece. And namely, the thing I have to realize here is 3x to the 4th plus 1 is always positive, right? Because this is an even power, and so whether the x happens to be negative or positive or 0, this thing is always non-negative, and then I add 1, and that makes it positive. Okay, but now 3x to the 4th plus 1 is strictly greater than 0, which is then greater than or equal to x to the 7th plus x. So putting that together, we have 3x to the 4th plus 1 is greater than 0, is greater than or equal to x to the 7th plus x. But then all we have to do is drop this middle part, and then we get the desired result. And, well, that's the thing we wanted to prove, so we're done. A lot of the times, there is realistically no way to prove a statement without switching it to the contrapositive and proving that. So it should be very high on your list of things to try. If you have a proof and you're struggling with it, you should definitely try writing down the contrapositive and see if maybe that's easier. Next, let's prove that if I multiply two integers together and get something even, it must be the case that one of the integers was even. The reason I'm including this is really that this includes another huge tip-off that you probably want to try the contrapositive. And that tip-off is this word or in the conclusion. Ors in the conclusion of something you're trying to prove are annoying. Because usually they mean that you have to sort of find secret cases somewhere to break it down so that you can figure out how this ends up working out. And that usually means you have to do something creative. But remember, the negation of an or is an and. And so if I write down the contrapositive of something with an or in the conclusion, I get something with an and in the hypothesis. And an and in the hypothesis is fantastic, because it means I get extra hypotheses. So, not universally the case, but it's a huge tip-off that if there's an or in the conclusion of your if-then statement, you should try the contrapositive. Of course, it is completely essential when you're employing proof by contrapositive that you write down the contrapositive correctly, because if you write down something that's not the contrapositive, even if you then prove it correctly, you have not actually done anything. Indeed, this is an annoying thing about proofs overall, is that if you have a proof that is correct in 95% of the places, the proof is still effectively completely wrong, because the proof only actually proves the thing you want to prove if every single step is correct. But in particular, if you're going to prove something by contrapositive, make extra sure you've written down the contrapositive correctly. In this instance, that is going to turn x is even or y is even into x and y are both odd, or x is odd and y is odd, if you prefer to write it that way. And it's going to turn x times y is even into x times y is odd. So we then can go ahead and suppose x and y are in Z, and both of them are odd. Then that guarantees me, by definition of odd, that both of these things can be written in the form 2k plus 1. But remember, I need to use different letters. So then, once I've done that, I can look at x times y. And then, so if I let, say, m be 2 times kl plus k plus l, then, of course, x times y is 2m plus 1, and so x times y is odd. And again, I've shown this if-then statement that I wanted to prove. So let's prove that if A and B are sets, and A union B equals B, then A is a subset of B. Again, this would be a great time. Pause the video, try and write this down yourself. Just practice writing up these proofs, because you're going to be writing down a lot of proofs by contrapositive this semester. Now, I'll note this is one of those things that's kind of annoying to prove, because it's, once you think about what it's saying, kind of obvious. And it's very tempting to write down a proof that says something like, well, this is kind of obvious because, and then sort of waves your hands all over, and you're not quite sure if you're done. Very often, proof by contrapositive is useful for taking something that you feel is kind of obvious but can't quite put into words, and turning it into something that's precise and indisputable. So, here is, I think, a great time to do that. So here's the contrapositive. If A is not a subset of B, then A union B is not B. Just a note about notation, please note there's a big difference between not a subset of and proper subset of. This is proper subset. That's not what I'm writing here. This is not a subset of, because the slash goes all the way through the symbol. Just be careful about that. It's easy to get those confused. Okay, so let's suppose B are sets, and A is not a subset of B. Here is where we get to practice our skills about negation. So A is not a subset of B. Well, what does A is a subset of B mean? A is a subset of B means for every x an element of A, x is also an element of B. So A is not a subset of B means you negate all of that. And so this becomes there exists x in A such that x is not an element of B. So let's spell that out. So there exists such that x is not an element of B. But I'm trying to show that A union B is not equal to B, and I'm very close to that. Because x is not an element of B, but x is an element of A union B. And that's just because x is an element of A. But if x is an element of this set, and x isn't an element of this set, then those two sets aren't equal. And that is what we wanted to prove. Okay, let's write down 3 real numbers. And let's prove that if it happens that the sum of those real numbers is greater than or equal to 6, then one of these 3 things must be true. The first number is at least 1, the second number is at least 2, or the third number is at least 3. Again, you might be tempted to kind of squint at this and be like, well, kind of if the biggest this could be was like 0.9 and 1.9 and whatever, and try and sort of like reason this out by kind of like guessing and checking, that's not really going to lead to a proof. Rather, again, these ors are telling us we should definitely try proof by contrapositive. And again, the contrapositive of this is going to be way nicer than the hypothesis. Because if the hypothesis I started with was, suppose x plus y plus z is greater than or equal to 6, it's not going to go well. And in this case, the contrapositive is actually so plain that I'm going to struggle to write down something for a proof of it. So let's try and be careful, though. Let's suppose x, y, and z are real numbers. Well, then what do? I can add these three inequalities together, and that will give me x plus y plus z is less than 1 plus 2 plus 3. And so x plus y plus z is less than 6, and we're done. I want to note, you might be tempted algebraically to jump straight to, okay, so this. But then if someone's reading this and they don't get it, they're really not going to have anything to hold on to. So this line here is written not really because I don't think the reader can add 1, 2, and 3 and get 6. It's written because including this line makes completely transparent what happened to these three inequalities. Okay, namely that x, that y, and that z went there, and that 1, that 2, and that 3 went there. So what work and algebra you show versus what work and algebra you skip in a proof can really help or hinder the reader understanding what is going on. So choose carefully when you're writing proofs to help make it as easy on the reader as possible, because when you're writing, that's the goal. One last example of proof by contrapositive for this video. And this is where we start pulling back into things about the division algorithm, because we're talking about things being multiples of 3, and anytime you see something about being a multiple of 3, 4, 5, etc., you should probably think, okay, maybe the division algorithm will be helpful here. So, again, I want to pause and think, what is it about this statement that would make you think contrapositive? Of course, you know I'm going to use the proof by contrapositive because it's the proof by contrapositive chapter. But let's imagine this wasn't the proof by contrapositive chapter. What is it about this that would tip you off? And the thing I think you should see to tip you off that this is going to be a proof by contrapositive is that the hypothesis here is about x cubed. And all the while the hypothesis is about x cubed, the conclusion is about x. And if you think back to all the direct proofs you've done, that sounds exactly backwards. I'd much rather know something about x than know something about x cubed. So let's see if this works. So here's our contrapositive. If x is not 2 more than a multiple of 3, then neither is x cubed. So let's suppose that x is in z, and x is not 2 more than a multiple of 3. So here's where it's very easy to get stuck, because this is not a helpful hypothesis by itself. In order to make this helpful, I have to use the division algorithm. So, by the division algorithm, and think for a second, what does the division algorithm say here? By the division algorithm, exists k and z such that x equals. Okay, and so remember, the division algorithm breaks numbers into 3 buckets. Multiple of 3, 1 more than a multiple of 3, 2 more than a multiple of 3. We've said not 2 more than a multiple of 3, so that means it is a multiple of 3, or it's 1 more than a multiple of 3. Now, note I have put an or into something that did not originally have an or in it. So that's arguably a little bit annoying. But we know how to handle this. We just handle these two possibilities separately. If x is 3k, we figure out what happens. If x is 3k plus 1, we figure out what happens. So if x is 3k, then x cubed is 3k cubed, which is 27k cubed, which is 3 times 9k cubed. And so what does that show us? That shows us, hey, x cubed is a multiple of 3. And remember, the buckets in the division algorithm are exclusive, so if I am a multiple of 3, I'm definitely not 2 more than a multiple of 3. So that handles that case. The other thing we wanted to nail down was what happens if x is 3k plus 1. Well, then x cubed is 3k plus 1 cubed. Then 3k plus 1 cubed is going to be 27k cubed plus 27k squared plus 9k plus 1. And so if, let's say, L is 9k cubed plus 9k squared plus 3k, then x cubed is 3L plus 1. And so x cubed is 1 more than a multiple of 3, and so not 2 more than a multiple of 3. And ta-da! That handles all the options. And so we have in fact shown what we were asked to show, which is that if x cubed is 2 more than a multiple of 3, then so is x. Throughout the remainder of the course, I promise you will see many, many, many more examples of proof by contrapositive. But hopefully this is enough now for you to get off to the races on the homework and to be ready for the test so that you can identify which proof or proofs on the test you should prove the contrapositive instead of the original statement, and that will set you off to a good place. But that's all for this week. I'll see you next week.